strong, flexible, and endlessly useful. Rope has been a tool of civilization for thousands of years. But how are ropes made today, in high-tech factories at industrial scale? Let's step inside a modern rope manufacturing facility to discover the journey from raw fibers to a neatly coiled rope ready for shipment. For thousands of years, humans relied entirely on nature to produce ropes. Even today, natural fibers are still used in many applications, prized for their biodegradability, rustic appearance, and grip. Let's look at the most common natural fibers. Sisal. Derived from the long, stiff leaves of the agave plant, sisal is coarse and rigid. It's ideal for ropes that need to hold shape or resist stretching, such as in agriculture or crafts. Its golden hue and rough texture make it popular for decorative uses too. Hemp, one of the oldest rope materials in history. Hemp fibers are strong, durable, and relatively smooth compared to sisal. Hemp ropes are still used for theatrical rigging, boating, and vintage-style applications. They're also resistant to UV light and rot, a rare trait for natural fibers. Cotton. Softer and more flexible, cotton ropes are typically used indoors or where comfort matters, such as pet toys, clotheslines, or decorative cords. However, cotton is weaker than other options and not well suited for outdoor or high-load use. Coir. Made from coconut husks, coir is the roughest of natural fibers. It's highly resistant to salt water and decay, making it suitable for marine ropes, mats, and erosion control nets. Each of these natural fibers arrives at the rope factory in compressed bales, often sourced from global agricultural suppliers. Before anything else, they're you. But nature has limitations. That's where science steps in. Modern rope production now leans heavily on synthetic fibers, which outperform natural materials in nearly every category: strength, durability, resistance to weather, and consistency. Let's break down the major players. Polypropylene, PP. Lightweight and cost-effective, polypropylene is one of the most commonly used fibers in the rope industry. It floats on water, resists mildew, and is used in everything from pool ropes to utility lines. However, it has low UV resistance and tends to degrade under sunlight unless treated. Nylon polyamide, known for its high tensile strength and excellent elasticity. Nylon ropes are perfect for dynamic loads like towing, climbing, or shock absorption. They're also abrasion resistant and long-lasting, but absorb water, which can weaken the rope when wet. Polyester. Strong, low stretch, and excellent at resisting UV, heat, and chemicals. Polyester ropes are often used for sailing, winching, or industrial tasks. Unlike nylon, it retains strength when wet, making it a top choice for marine and outdoor use. Kevlar, aramid fibers, incredibly strong and heat-resistant. Kevlar ropes are used in specialized fields like aerospace, military, or fire rescue. They can handle extreme tension and temperature, but are costly and less flexible than other options. These synthetic fibers arrive at the factory in pre-extruded filaments or on large industrial spools. Everything is now set for the next stage, fiber preparation, where these raw threads begin to take shape as structured yarns. At first glance, a bale of raw fiber looks like chaos. Whether it's natural strands fresh from the earth or synthetic filaments extruded by machines, the material is loose, tangled, and shapeless. There's no strength yet, no direction, just potential. The carding removes debris, seeds, and short strands, allowing only the strongest, most uniform fibers to move forward. And for coarse materials like coir, the process is adjusted to handle the rougher texture without breaking it apart. Next comes drawing, a dance of tension and precision. Here, multiple slivers are pulled together and gently stretched, blending into one long, even strand. Each pass through the drawing frame doubles the length while refining the thickness, smoothing inconsistencies, and equalizing density. If the final product demands high strength or delicate texture, like a climbing rope or marine line, the fibers may go through combing as well. This extra refinement strips out shorter fibers and imperfections, leaving only the longest, most resilient filaments behind. This stage is quiet but crucial, because no matter how advanced the machinery that comes later, if the fibers aren't right here, the rope won't hold when it matters most. And now the transformation deepens. We move to spinning, a process that feels ancient, even in today's high-tech factories. It's a moment where art and engineering meet. Slivers are fed into high-speed spinning machines, where they are twisted into yarn. The twist is what binds them, adding strength, resilience, and shape. It's here that each strand becomes more than a collection of threads. It becomes unified. It becomes strong. Depending on the rope's intended use, the machines adjust the twist per inch TPI to deliver the right balance of tension and flexibility. A tightly twisted yarn offers strength and low stretch. A looser twist offers softness and pliability. For natural fibers, this process honors centuries of craftsmanship, modernized, accelerated, but still rooted in something timeless. But in synthetic rope production, spinning takes a different shape. Instead of slivers, synthetic ropes begin with plastic pellets, usually polypropylene, nylon, or polyester. These are melted and extruded through tiny holes in a metal disc called a spinneret, forming long, continuous filaments. As they emerge, the filaments are cooled, stretched, and bundled into yarn-like strands. These synthetic yarns can be miles long, consistent to the micrometer, and ready for any environment, sea, sky, or steel beam. Once spun, whether by nature or chemistry, all yarns are wound onto large bobbins, sleek, orderly, and ready for what comes next. Each bobbin is marked with its specifications: material type, twist direction, batch number. They are stacked on creels, ready to feed into the twisting and braiding machines that will give them their final form. In this moment, the factory is quiet. Rows of bobbins stand like sentinels, each holding the quiet energy of what's to come. From the chaos of raw fiber to the discipline of spun yarn, rope is no longer just imagined. It's beginning to breathe. With yarns now spun, wound, and ready, it's time for the defining moment in rope manufacturing: twisting. Twisting is what transforms a handful of soft, individual yarns into a single, unified rope, one that's strong, flexible, and built to last. This step is where the rope truly comes to life. The process begins with stranding. In this stage, multiple yarns are grouped together and twisted into larger units called strands. These strands act as the building blocks of the final rope. Depending on the design, each strand might consist of dozens, even hundreds of yarns, depending on the intended strength and thickness of the rope. These yarns are loaded onto large motorized frames called stranding machines. Each machine rotates the yarns in a single direction, either clockwise or counterclockwise, applying a controlled and consistent twist, known as an S-twist or Z-twist. This direction matters because in the next stage, the strands will be twisted in the opposite direction to balance out internal tension. Without this reversal, the rope would unravel under load or spin awkwardly during use. Once the strands are formed, they are routed into a rope-laying machine, a larger, more complex version of the strander that assembles the final product. Here, the strands are twisted together in the opposite direction of their individual yarns, an engineering principle known as counter-twisting. For example, if each strand was twisted clockwise, the machine will twist the strands together counterclockwise. The rope has form now, strands woven, tension balanced, but it hasn't yet been tempered. Like forged steel, it must be set. For synthetic ropes, this begins in the heat tunnel, where warm air or steam stabilizes the twist, locks in memory, and smooths out minor imperfections. It's a moment of quiet transformation, where the rope sheds its last traces of instability. Next comes coating. Some ropes receive a fine mist of UV-resistant spray, protecting them from years under the sun. Others are dipped in abrasion-resistant finishes, designed to survive saltwater, concrete, or steel. Color threads are woven in, barcodes attached, batch numbers logged. Every rope now carries its own identity. It's no longer just rope, it's field-ready, trusted to lift, hold, save, and endure. Before a rope can serve, it must prove itself. In the testing lab, samples are clamped into tensile machines, massive arms that pull until the rope snaps. Every breakpoint is recorded, measured in kilonewtons, and checked against strict load ratings. No guesswork. no exceptions. Next is abrasion testing, where ropes are dragged across steel bars, simulating years of wear in minutes. Then comes chemical and water resistance, especially for ropes used at sea, in factories, or in rescue gear. Some ropes are even tested in extreme temperatures, from freezing cold to desert heat. Only ropes that pass every test, strength, durability, resilience, are cleared for packaging. The rest are rejected without compromise. Because when a rope is called upon, failure is not an option. From tangled fibers to precision-woven strands, every rope carries more than strength. It carries trust. Trust that it will hold when the storm rages. Trust that it will catch when gravity calls. Trust that, unseen, it will keep our world from falling apart. Rope is one of humanity's oldest tools, yet it evolves with us. Tougher, smarter, lighter. Behind every line thrown from a ship, every lifeline lowered from a cliff, every tension cable holding a bridge, is a process built on patience, precision, and purpose. In every factory coil lies a silent promise: I will hold. If you found this journey fascinating, don't forget to like, subscribe, and tap the bell icon, because every week we explore the hidden stories behind the everyday things that shape our world. This is how it's made, and this is just the beginning.